3.3.3, it looks beautiful. It will be beautiful. I love tangent, personally. Tangent's my favorite trig function. Also because arctangent is the nicest inverse trig function, I think. Okay, so we're just doing another example. Example 2. I want you to integrate square roots. Nope, that's not it. 1 divided by the square root of 1 plus x squared. This is almost inverse tangent. If there were no square root, this would just be arctan of x plus c. Because there's a square root, there's a problem. If this were a minus sign, it'd just be arc sine. But it's not. I want you to always think about this though. I don't want you doing trig subs if you don't have to do trig subs. Obviously in this section, we're teaching trig subs, so we're going to be doing a lot of trig subs. But always think of your options. You have so many options in this class, and the more and more this class goes on, the more you have options. And unfortunately, options are usually bad. They give us more power, but they take more thinking. U substitution is not really going to work here because you get that dx is like 1 over 2x, and then it's hard to translate that x back into u. You could try it, but it's not really going to go anywhere. I don't think integration by parts is good as well. There might be some world where integration by parts works. I think it's going to end up with an integral with like x squared over the same square root. And if we had an x on the top, that'd be helpful. But an x squared on the top is going to give us the same problems as before. So integration by parts doesn't really work. I just want you to kind of always be thinking about these things. But of course, we're doing a trig sub here because I'm trying to teach you about trig subs. So remember, oh, how far back was this? These are the three, these red identities are the 3 identities that we're really thinking about in this section. Obviously, there's a hint up here, but I want you to look at why is 1 plus x squared have to do with tangent? It's because of this. We're letting x be some trig function. So if this is x squared, then x squared plus 1 gets rid of the addition. That's really what we're all about here. Addition and subtraction inside square roots is terrible. So if we use these things, then we're left with the right-hand side, which has no addition and subtraction, and we can simplify that square root. So again, we remember that 1 plus tangent squared of any angle is secant squared of any angle, and we want to get that here. So we'll let x, we don't need any multiples here. We can just let x be tangent of theta directly. And then dx will be its derivative. Derivative of tangent is secant squared of theta dx. Now let's think about domains. What can x be here? Well, it's in a square root, so we want the square root to be positive. But this will always be positive. We have a square root, it's in the denominator, so we don't want it equal to 0. Well, this will never be 0. This is always at least 1. So x is actually anything when we think about our domain. So what is theta going to be? Remember the graph of theta. Or the graph of tangent, rather. It looks like this, and then it repeats forever. So if the output, x is the range of tangent, to get an output of anything, what does theta have to be? Well, if theta, notice if theta is negative pi over 2 to pi over 2, exclusive, that's just this whole first piece. And this does cover every single output, right? The range in this interval is all real numbers. So that's perfect. So let's hope that this knowledge of what theta has to be makes things easier going forwards. Let's do that sub. We've got 1 over 1 plus x squared is going to be tangent squared of theta. What is dx? It's secant squared of theta. Whoa, I made a mistake. Hopefully you caught it. This should be a d theta over here. And now we simplify. This becomes, well, we know 1 plus tangent squared of any angle is the secant squared of that angle. And we have a secant squared over here. And then the square root of something squared is its absolute value. So the question is, what do we know about secant of theta on this interval? Secant is 1 over cosine. So if cosine's positive, secant's positive. Right? Secant of theta is 1 over cosine of theta. And just like in the last two videos, we know from negative pi over 2 to pi over 2 that cosine of theta, well, is strictly positive here. Because we have exclusive. Cosine of theta will never equal 0, which is good, because if cosine of theta equals 0, we've got a problem. Cosine of theta equals 0, big problem. So, whew, great. Secant of theta is its absolute value on this region. And that is rather nice. We won't have that all the time, but we will have it for these tangent subs. So since secant of theta is equal to its absolute value, this does cancel to just be secant theta. Okay? Because again, here on this interval, the absolute value of secant of theta is equal to secant of theta. So what's the antiderivative of secant? Well, we can find it with integration by parts, I think. Or maybe it wasn't in it. Maybe it's a u sub. I don't remember how we do this integral. Secant is 1 over cosine. Yeah, I want to say you do integration by parts. But what you're going to get is that it's the natural log of the absolute value of secant theta plus tangent theta plus c. Pretty sure. We'll check that at the end. And then, again, we have to put everything in terms of x. So remember, x was tangent of theta. Okay, so this part is just x. That's great. What's secant of theta? No clue. And again, it doesn't matter. We won't always have this. It doesn't matter whether theta is positive or negative, because secant will be always positive in the first or fourth quadrant. Tangent of theta is opposite over adjacent. Opposite over adjacent is like this. This becomes the square root of 1 plus x squared. Oh, okay. So that tells us that cosine of theta, this is an intermediate step that I like. You don't need it. Cosine of theta is adjacent over opposite. So secant of theta is that reciprocal. So we get the natural log of the absolute value of the square root of 1 plus x squared plus tangent of theta, which is just x, plus c. And now we have a really interesting question that I did not foresee. And the question is, are these absolute values necessary? X can be positive or negative, but we know this is always positive. So the question is this bigger than x? Right? If the square root of 1 plus x squared is bigger than x, then we don't need the absolute values. Why? We don't need the absolute values because even if x is negative, this part will be bigger, more positive. So if this, then we don't need the absolute values. So the question is this true? If you square something and add 1 and then take the square root, is it always bigger? Yeah, it is. Right? And there's a couple of ways of showing that. I don't know if I really want you guys to have to prove it. But yeah, so okay. So here's one of the ideas. This is inarguably true. Right? If you add 1 to something, it's bigger. Always. Doesn't matter what x is. Now, if I take the square root of something that's bigger, the result is still going to be bigger. Notice that this is not the same as just squaring this. You have to start with something you know to be true and get to something you want to prove. You can't go the other way. And then again, as long as x is positive, this is the same, and that's what I wanted to show. And if x is negative, it's still true anyway. So regardless, this is true. We do not need the absolute values. So our fully simplified answer actually looks like this. There we go. That's our answer. We could check our answer using a derivative. We should also make sure that Jason's using the right integration formula for secant. Yeah, it is. Natural log of secant plus tangent. All right, great. There are actually a couple of different ones. This is the one that we're using. There we go. That's the answer. You can check your work. Yeah, we'll check it together. This is the end of the video. Go away. Pause the video. Close it, whatever. But if you want to see me check my answer, you can stick around. But the video is over. All right, if we take the derivative, what do we get? Derivative of natural log is 1 over the inside times the derivative of the inside. Chain rule requires that this becomes a 2x up here. That's the whole derivative of the inside. Okay, let's see where this goes. Well, good algebra practice on these ones. This is 1 over the square root of 1 plus x squared plus x times, we can't multiply fractions yet because we need a common denominator. So we're going to write this 1 as 2 root 1 plus x squared over 2 root 1 plus x squared. Now we can combine those fractions. 2x plus 2 square root of 1 plus x squared. And then over 2 square root of 1 plus x squared. Great. Now we can multiply these fractions. The top is easy. I'm going to factor out a 2 because we're probably going to need it factored. I don't know if it's true, but I'm assuming it will be true. And the bottom, we will we'll distribute that. Maybe. Do we want to distribute? Usually we want to keep it factored. We keep it factored if we want to cancel. We distribute it if we want to combine like terms. But notice one of our factors in the bottom is also a factor in the top. Let's keep it factored. And we'll get this. This factor is equal to that factor. This factor is equal to that factor. Woo, we did it. These ones really make me nervous because there's a lot of algebra. And it's kind of hard to see where it's going to... Really, really good practice to check your answers on these ones. I'm glad I did it. So again, that's what we wanted. Check our answer. Take the derivative of our antiderivative, and we should get our original integrand. Nice. Good algebra here, man. It's been a while since I've done some good algebra. I'm not a big algebra lover, but it kind of, you know, kind of pumps me up a little bit. Hope you guys like algebra too. Anyway, that's it for the video. Bye-bye.